Crossing the Milky Way galaxy sounds like a journey. It sounds like something advanced humans will eventually achieve. But here is the truth. It is not just difficult. It is physically impossible within a single human lifetime. Even light, the fastest thing in the universe, cannot do it quickly. Light moves at 300,000 kilometers every second. It can circle the Earth more than 7 times in a single second. Nothing travels faster, nothing even comes close. And yet, to cross the Milky Way, light needs more than 100,000 years. That is not a guess, that is not a limitation of technology, that is the actual scale of our galaxy. Now think about what that means. If the fastest thing that exists needs 100,000 years, then where does that leave us? The real question is not how we will do it, the real question is why it is impossible at all. Because most people assume the problem is simple: build a faster spaceship, improve engines, use better fuel, wait long enough, and humanity will solve it. But that assumption is completely wrong. The barrier is not engineering, the barrier is reality itself. The Milky Way is not just big, it is overwhelmingly large in a way that the human brain struggles to understand. It contains hundreds of billions of stars. Entire solar systems exist between those stars. Vast, empty regions stretch across distances that cannot be measured in any familiar way. Our own location is not special. Earth sits in a quiet corner of this galaxy about 26,000 light years away from the center. That already means that even reaching the center would take tens of thousands of years at the speed of light. And crossing from one side to the other is far beyond that. This is where things become unsettling. Because even if humanity somehow builds a spacecraft that moves close to the speed of light, the problem does not disappear, it becomes worse. As speed increases, strange effects begin to take over. Time itself starts to change. Distances begin to behave differently depending on who is observing them. The faster you move, the more the universe distorts around you. These are not science fiction ideas. These are real effects described by Albert Einstein in his theory of relativity, and they have been tested again and again. Later, physicists like Greene helped explain these ideas in a way that reveals something deeper. The universe is not just large, it is structured in a way that places hard limits on what is possible, limits that cannot be broken, limits that no technology can overcome, limits that no technology can overcome, because the closer you try to get to the speed of light, the more energy you need. Not a little more, not double. The requirement increases dramatically, approaching infinity. That means no matter how advanced a civilization becomes, it can never reach that ultimate speed, and without reaching it, crossing the Milky Way in a human lifetime remains out of reach. But the story does not end there. There are other problems. Problems that most people never consider. Space is not empty. At extreme speeds, even tiny particles become deadly. A single grain of dust can hit with the force of an explosion. Radiation becomes more intense. The environment itself turns hostile in ways that cannot be easily avoided. Then comes the question of time. Because even if you could somehow survive the journey, time would not behave the way you expect. For the traveler, the trip might feel shorter, but for everyone else, thousands of years would pass. You would not return to the world you left. You would not return to your time. You would arrive in a future that no longer belongs to you. So this is not just a problem of distance, it is a problem of physics, of energy, of survival, of time itself. And when all of these limits come together, they form a wall that cannot be crossed. In this video, you will understand exactly why crossing the Milky Way in one lifetime is impossible. You will see how the size of our galaxy creates a challenge that no machine can solve. You will learn why the speed of light acts as a barrier that nothing can break. You will explore how time itself changes at extreme speeds. And you will discover the hidden dangers of interstellar travel that make the journey even more unforgiving. Most importantly, you will realize that this is not about a lack of progress. It is about the fundamental rules of the universe, rules that define what can and cannot happen. And once you see those rules clearly, the idea of crossing the galaxy begins to feel less like a dream and more like a boundary that was never meant to be crossed. Welcome to the channel. If you want to explore the deepest ideas about space, reality, and the limits of the universe, make sure to subscribe and stay with us. The Milky Way galaxy is not just large, It is overwhelmingly vast in a way that breaks normal thinking. Its diameter stretches beyond 100,000 light years. That number sounds simple, but it hides something deeper. 1 light year is the distance light travels in a full year. Light moves at 300,000 kilometers every second, and still, it takes more than 100,000 years to cross from one side of this galaxy to the other. That is the scale. Inside this enormous structure, there are hundreds of billions of stars. Each one could have its own system of planets. Some of those planets could be like Earth, some could be completely alien. All of them are separated by distances so large that even the nearest stars are several light years apart. This means that even the space between stars is already a massive journey. Now consider where we are. Earth sits far from the center of the galaxy, roughly 26,000 light years away. That places us in a quiet outer region far from the dense core. Even reaching the center alone would take longer than the entire history of human civilization multiplied many times, and crossing the galaxy means going far beyond that. It means starting from one edge and reaching the other, not just moving between nearby stars, but traveling across the full width of this cosmic structure. That distance is not straight or simple either. The galaxy is not a flat disk in a simple sense. It has spiral arms. It has regions filled with gas, dust, and dark matter. Some areas are dense and chaotic. Others are nearly empty. The path across it is not a straight line through empty space. It is a journey through a complex and shifting environment. Even more surprising, most of the galaxy is dark. Not dark in the sense of empty, but filled with matter that does not emit light. Scientists call this dark matter. It makes up a large portion of the galaxy's mass. It shapes the structure of the Milky Way, yet it remains invisible and mysterious. So when people talk about crossing the galaxy, they are not just talking about distance. They are talking about moving through a vast and largely unknown system. And even the concept of crossing becomes difficult to define. From where to where, from our position to the opposite edge, from one spiral arm to another, from the outer rim through the center and out again, each version still involves tens of thousands to over 100,000 light years, numbers that go far beyond any journey humanity has ever attempted. The farthest human-made object, the Voyager probes, haven't been traveling for decades, and they have not even come close to leaving our local region of space. They are still within the influence of our own star system. That is how small our current reach is compared to the scale of the Milky Way. So the problem begins here, before speed, before energy, before survival. It begins with size, a size so vast that even defining the journey already pushes the limits of what is physically meaningful. And once that scale is understood, the next barrier starts to reveal itself. There is a rule in this universe that nothing can break. It does not depend on technology. It does not change with time. It is fixed into the structure of reality itself. This rule is the speed of light. Light travels at about 300,000 kilometers every second. That is fast enough to circle Earth more than 7 times in 1 second. It can go from the moon to Earth in just over a second, from the sun to Earth in about 8 minutes. This speed is not just fast, it is the maximum speed anything can ever reach. Not almost anything, not with better engines. Nothing. Objects with mass are locked below this limit forever. This idea comes from Einstein's theory of relativity. It shows that as an object moves faster, its mass effectively increases, not in a simple way, but in a way that resists further acceleration. The faster you go, the harder it becomes to go even faster. At low speeds, this effect is small. It is invisible in daily life. But as speed approaches the speed of light, the effect becomes extreme. Energy requirements begin to explode. To double your speed at normal conditions, you need more energy. But near light speed, adding even a tiny increase in speed demands enormous energy. The closer you get, the more dramatic the increase becomes. It does not rise steadily, it rises sharply, then it rises again even faster. At the exact speed of light, the energy required becomes infinite. That is the barrier. It is not that humans have not built a fast enough engine, it is that the universe does not allow it. Even the most powerful events in nature respect this limit. Exploding stars, colliding black holes, high-energy particles traveling across the cosmos. None of them exceed the speed of light. In particle accelerators on Earth, scientists push particles to extreme speeds. These particles come very close to light speed, closer than anything else humans had ever created. But even then, they never reach it. No matter how much energy is added, the final limit remains just out of reach. This creates a strange situation. You can get closer and closer to the ultimate speed, but you can never arrive there. And even getting close is not easy. To move a spacecraft at a significant fraction of light speed would require energy on a scale that rivals entire planets. The fuel alone becomes a problem. Carrying that fuel adds mass, which then requires even more energy to accelerate. It becomes a loop that grows out of control. Even advanced ideas like antimatter propulsion face the same issue. They can provide more energy, but they do not remove the limit. They only bring you closer to it. And being close is not enough, because when distances are measured in tens of thousands of light years, even a small difference in speed means a massive difference in travel time. Traveling at 10% of light speed would still take hundreds of thousands of years to cross the galaxy. Even at 90%, the journey remains far beyond a human lifetime. This is where the true weight of the problem begins to show. It is not about building something faster. It is about facing a rule that cannot be broken, a limit that applies everywhere. And once this limit is understood, another strange effect begins to emerge. As speed increases and approaches the ultimate limit, something strange begins to happen, not to the engine, not to the fuel, to time itself. This effect is called time dilation. It comes directly from Einstein's theory of relativity, and it changes the way motion and time are connected. At low speeds, time feels constant. 1 second is always 1 second. But as an object moves faster, especially close to the speed of light, time for that object begins to slow down relative to everything else. This is not an illusion. It is real. It has been measured with precise atomic clocks. Clocks placed on fast-moving aircraft tick slightly slower than those on the ground. Particles moving at high speeds inside accelerators live longer than expected because their internal clocks slow down. The faster the motion, the stronger the effect. At speeds close to light, time can slow dramatically. For a traveler moving near this limit, seconds pass normally. Their heartbeat feels the same. Their thoughts move at the same pace. Nothing inside their body feels different, but outside, everything changes. Years begin to pass quickly, then decades, then centuries. From the perspective of the rest of the universe, the traveler is moving through time at a slower rate. This creates a strange kind of shortcut. If a spacecraft could move close enough to light speed, the travelers inside might experience a journey that feels much shorter than it actually is. A trip that takes thousands of years in the outside universe could feel like only a few years to them. This sounds like a solution. It sounds like a way to cross vast distances within a human lifetime. But this is where the deeper truth appears. The distance itself does not change. The galaxy remains just as large. The path remains just as long. The ship still needs to travel every part of that distance. Time dilation does not shrink space. It only changes how E is experienced by the traveler. From the outside, the journey still takes tens of thousands of years. Civilizations rise and fall. Stars move through their orbits. Entire histories unfold. When the traveler finally arrives, they do not step into the world they left behind. They step into a distant future. Everyone they knew is gone. Everything familiar has changed. Even more unsettling, this effect works both ways depending on perspective. To an observer watching from Earth, the traveler seems to age slowly. To the traveler, it is the rest of the universe that appears to speed forward in time. Both views are correct at the same time. This is one of the most surprising features of relativity. Time is not universal. It depends on motion. So even if technology could push a spacecraft close to light speed, and even if the travelers could survive the journey, they are not escaping the limits of the galaxy. They are only changing how they experience the passage of time. The journey remains just as long in the fabric of the universe, and reaching those extreme speeds introduces another problem that grows rapidly as velocity increases. Speed is not the only barrier. Energy stands in the way, and it grows into something far more unforgiving as velocity increases. To move any object, energy is required. That is a simple rule. A small push moves a small mass at a low speed, but when the goal is to push a massive spacecraft to extreme speeds, the numbers begin to rise very quickly. At first, the increase seems manageable. Doubling the speed requires more energy. That makes sense. But as the spacecraft moves faster and faster, something deeper begins to happen. The energy does not increase in a straight line. It rises faster than expected. Then it rises even faster again. As the speed approaches the speed of light, the required energy begins to grow toward infinity. This is not a technical problem. It is not a limitation of engines or fuel design. It is a direct consequence of Einstein's theory of relativity. The closer the spacecraft gets to light speed, the more it resists further acceleration. It becomes harder and harder to push it faster. Each small increase in speed demands a massive increase in energy. At some point, adding even a tiny fraction of speed would require more energy than entire planets can produce. This creates a wall that cannot be crossed. Even reaching a fraction of light speed is already beyond current human capability. To accelerate a spacecraft carrying humans to just 10% of light speed would require an energy output comparable to the total energy consumption of entire civilizations over long periods of time. And that is only the beginning. To reach 50%, the energy demand rises dramatically. To reach 90%, it becomes extreme. Beyond that, it starts to approach levels that are no longer realistic in any sense. Then there is another hidden problem. Fuel has mass. To carry fuel for acceleration, the spacecraft becomes heavier. A heavier spacecraft needs more energy to accelerate. That requires more fuel. More fuel adds more mass again. This loop grows quickly. It becomes a chain reaction that pushes the energy requirement higher and higher. Even theoretical solutions struggle with this. Antimatter is often described as the most powerful fuel possible. When matter and antimatter meet, they convert mass directly into energy. This is the most efficient process known in physics, but even antimatter does not solve the problem. Producing it requires enormous energy. Storing it safely is extremely difficult. And even if large amounts could be used, the fundamental limit remains. It only delays the barrier. It does not remove it. There are also proposals involving light sails powered by mass. I've lasers from distant points. These ideas remove the need to carry fuel, but they introduce new challenges. The energy still has to come from somewhere. The infrastructure required would be enormous. And even then, reaching near light speed for a large human-carrying spacecraft remains far beyond realistic limits. Nature itself gives a clue about how extreme these energies are. High-energy cosmic rays travel through space at speeds close to light. Some of them carry as much energy as a fast-moving baseball packed into a single particle. These are among the most energetic particles ever observed. And even they do not reach the ultimate speed. This shows how difficult it is to approach that limit, even for the smallest pieces of matter. Now scale that challenge up to an entire spacecraft, a structure large enough to support life, shielding mass. The energy required becomes overwhelming, and this is only the cost of motion. It does not include the cost of surviving what comes next. Space looks calm from a distance. It looks empty, silent, safe. But that is not the reality a fast-moving spacecraft would face. Interstellar space is filled with particles. Most are tiny, single atoms, dust grains, fragments left behind by stars. At normal speeds, these particles are harmless. A spacecraft moving slowly would barely notice them, but speed changes everything. At velocities approaching the speed of light, even the smallest particle becomes a threat. A single atom can strike with enormous energy. A grain of dust can hit with the force of an explosion. This happens because energy depends on speed. As velocity increases, the energy of impact rises dramatically. Near light speed, the energy released in a collision becomes extreme. A tiny particle can punch through metal. It can damage critical systems. It can tear through protective layers that are designed for far weaker impacts. Now consider the density of space. Even though it is sparse, over long distances, collisions become unavoidable. A journey across the galaxy would pass through regions filled with gas clouds, dust streams, and remnants of ancient stars. Each encounter adds risk, and the faster the spacecraft moves, the more dangerous every collision becomes. Shielding becomes a serious challenge. Thick layers of material could provide some protection, but they add mass. More mass requires more energy to accelerate. The problem returns again. Some ideas suggest using magnetic fields to deflect charged particles. This could help against certain types of radiation. But not all particles carry charge. Neutral atoms and larger dust grains would still pass through. There is no simple shield against everything. Then there is radiation. Space is already filled with high-energy radiation from distant stars, supernova explosions, and cosmic rays. On Earth, the atmosphere and magnetic field protect life from most of it. In deep space, that protection is gone. At high speeds, the situation becomes worse. Radiation from the front of the spacecraft becomes concentrated. It builds up like a storm. Particles strike with greater energy. The intensity increases. Some scientists describe this effect as a form of radiation wall forming in front of a fast-moving object. Exposure to such radiation would be dangerous for any biological system. Human cells are sensitive. DNA can be damaged by high-energy particles. Long-term exposure increases the risk of cancer, organ failure, and other serious conditions. Even short exposure to intense radiation can be lethal. Protecting against this would require heavy shielding, again, more mass, more energy, more difficulty. And then there is the human body itself. The body is designed for Earth, for gravity, for a stable environment, for moderate speed. EDS. Extreme acceleration places stress on organs, blood flow changes, internal systems struggle to adapt. Prolonged exposure to such conditions is not well understood. Even if acceleration is controlled, the long duration of the journey introduces new problems. Isolation, closed environments, limited resources, psychological strain. A journey lasting years for the traveler could still involve conditions that are difficult to sustain, and this is under the best possible scenario. Now combine all of these factors: high-speed impacts, intense radiation, biological limits. The environment itself becomes hostile, not because of one single danger, but because of many dangers acting together. And even if solutions are proposed for each individual problem, they begin to conflict with one another. Protection adds mass. Mass increases energy demands. Energy demands push speeds higher. Higher speeds increase danger again. It becomes a cycle that is difficult to escape. And this is still within the framework of known physics. Beyond this, there are ideas that attempt to bypass these limits entirely. When the limits of speed, energy, and survival become clearer, the mind searches for a way around them. This is where the most famous ideas appear: wormholes, warp drives, shortcuts through space itself. They sound like solutions. They promise to bypass distance instead of fighting it. A wormhole is often described as a tunnel connecting two distant points in space. Instead of traveling across the galaxy, a spacecraft would enter one end and exit somewhere far away. In theory, the journey could take moments. The idea comes from the mathematics of Einstein's theory of relativity. The equations allow for such structures under certain conditions. They are not pure fantasy. They exist as solutions on paper.
But there is a problem. Every known version of a stable wormhole requires something
Called exotic matter. This is not normal matter. It would need negative energy density, something that behaves in a way opposite to everything observed in everyday physics. So far, no one has found a real form of matter like this in usable amounts. Tiny effects related to negative energy appear in quantum physics, but they are extremely small and unstable. They cannot be scaled up to hold open a tunnel across space. Without this exotic matter, a wormhole would collapse instantly. Even if it could exist, keeping it stable would be another challenge. The slightest disturbance could cause it to snap shut. Anything inside would be lost. Then there is the warp drive. This idea suggests bending space itself. Instead of moving a spacecraft through space, space around the craft would contract in front and expand behind. The ship would ride inside a bubble, effectively moving faster than light relative to distant points, while locally remaining at rest. It sounds like a perfect solution. And again, the mathematics allows for it, but the requirements are extreme. Early calculations showed that a warp bubble would need an amount of energy comparable to the mass of entire planets, or even stars. Later refinements reduce this number, but it remains enormous. And the same problem returns. Exotic matter is still required. Negative energy, unknown physics, conditions that have never been created or controlled. There are also stability issues. A warp bubble could be unstable. It could collapse suddenly. It could generate intense radiation when it forms or when it stops. Some models suggest that energy could build up at the front of the bubble and release in a burst that would destroy anything in its path. Even controlling direction and speed becomes uncertain. Then there is another hidden issue. Both wormholes and warp drives may create problems with causality. They could all allow effects to happen before causes. This leads to paradoxes, situations where the order of events breaks down. Many physicists believe that the laws of the universe prevent such scenarios from becoming real. So even though these ideas are allowed in equations, reality may block them. Right now, there is no experiment that shows a working wormhole, no test that proves a warp drive can exist, no technology that brings these concepts closer to practical use. They remain mathematical possibilities. They are powerful tools for understanding the limits of physics, but they are not engineering solutions. And as these last hopes begin to fade, the full weight of the problem becomes clear. Crossing the Milky Way galaxy in one lifetime is not a challenge waiting to be solved. It is a limit that already exists. The distance is too vast. The speeds required are locked behind an unbreakable rule. The energy needed grows beyond anything we can produce. And even if those barriers could be pushed aside, the human body would still face an environment it was never meant to survive. All of these limits come together, not as separate problems, but as one system that closes every path. This is the deeper truth. The universe is not just large. It is structured in a way that defines what is possible and what is not. These rules are not suggestions. They are built into the fabric of reality, and they apply everywhere. Even the most advanced civilizations, no matter how far they evolved, would face the same boundaries, the same speed limit, the same energy wall, the same dangers hidden in empty space. This changes how the galaxy should be seen, not as a place waiting to be explored from edge to edge, but as a vast system where distance itself becomes a barrier that cannot be crossed within a human life. There is something both humbling and unsettling in that idea. Humanity is not just separated by space. It is separated by the laws that shape space and time, and those laws do not bend easily. If this perspective shifted the way you see the universe, take a moment to support the channel. Like the video and subscribe for more deep explorations into space, physics, and the limits of reality. Because the more these limits are understood, the clearer one truth becomes. We are not only confined by how far things are, we are confined by what the universe allows.